Now it's time to do some gravity problems. Let's go ahead and do this problem. A robot drops a solar panel off the rim of a 402-meter high cliff on Mars, where the free fall acceleration is 3.7 meters per second squared. Part A, calculate the velocity with which the solar panel hits the ground. And part B, calculate the time required for the solar panel to hit the ground. All right, so there's a lot of good stuff in this problem, and we'll address each one of those things piece by piece. But let's go ahead and draw a diagram so that we're all on the same page. All right, so a robot drops a solar panel off the rim of a 402-meter high cliff on Mars. Well, let's go ahead and draw that. So here's the solar panel. I'm going to illustrate it with a big dot point mass, and it goes straight down towards the surface of Mars. And the displacement from here to here is going to be 402 meters. Now I made that positive, even though I'm below my initial starting position. So let's talk about that there, because some people might make that negative 402, and that might be right? Depending on how they set up the problem, that could be right. What I like to do is make my initial direction of motion positive. So the solar panel's initial direction of motion when it was dropped was down. So I'm going to make down positive. Let's just think about that. Usually in math, you got your Cartesian coordinate plane, and usually, to the right, here's the origin. To the right's going to be positive, to the left's going to be negative. Up is going to be positive, down is going to be negative. And that's fine. And we can do that in science too. But sometimes to make the math a little bit easier, what we can do is we can actually take this and then just rotate it 180 degrees. So now down is going to be positive and up is going to be negative. And you can do this for left and right also, right? You can define your axes however you want. If you do make down positive, like I'm going to do here, then up becomes negative. So keep that in mind. So I'm making down positive, and I am, the solar panel is going down in a downward length. So it's going to be positive 402 because I'm making downward positive. All right, let's go a little bit further with that idea. All right, so the initial velocity when that solar panel is dropped, just like this, is going to be 0. It's going to be 0. We're starting from 0, and we want to find, and be careful here, because some people will say, oh, that's a trick problem. How fast is it going when it hits the ground? Easy. It hit the ground, it's going 0. That's not what we mean in physics, all right? We're not trying to trick you there. What that actually means is when we say how fast is the solar panel going when it hits the ground, is we really mean is how fast is it going a split second before it hits the ground. That's what we're looking for. That's what we're looking for. And we also have the acceleration due to gravity. Now, we're on Mars, so that acceleration due to gravity is going to be a little bit different. In fact, it's going to be about 1/3 of what it is on Earth. On Earth, it's 9.81, but on Mars, it's going to be a little bit different. It's going to be 3.7 meters per second squared. And again, I'm going to make this positive because gravity is always trying to pull things down towards the surface of, in this case, Mars. So gravity's trying to pull it down. And I remember I defined down as positive. So I'm going to leave that as positive. Let's see, do we got anything else? I think that is it. I think that's it. We've got our known information and our unknown information. Don't forget this, the problem doesn't always tell you what the acceleration due to gravity is, especially on Earth. They just assume 9.81. So that's kind of a piece of information that sometimes you won't be given, but if you're on Earth, it's 9.81 meters per second squared. All right, let's go ahead and solve this problem. You want to look at your equations. Obviously, you need velocity final in the equation. And again, always remember that delta V is actually final minus initial in disguise, and average velocity is initial plus final divided by 2 in disguise. So don't rule those out. Now, the equation I'm going to use is this one right here. Velocity final squared equals velocity initial squared plus 2ax. We're looking for that final velocity, so there it is. And the initial velocity is going to be 0 plus 2. The average acceleration is going to be 3.7 meters per second squared. So it's speeding up about 1/3 as quickly as it would on Earth. So again, it kind of looks like it's speeding up in slow motion on Mars. And the displacement is 402 meters. What I want to do is I want to multiply these three together, but be careful. I want velocity final, not velocity final squared. So in order to get from here to here, I got to take the square root of both sides, because what I do to one side, I got to do to the other side too. So multiply these three together, whatever that number is, take the square root of it, and when you do that and you round off, you're going to get 55 meters per second. So 55 meters per second. There we go, 2 significant digits. All right, part C, calculate the time required for the solar panel to hit the ground. Again, you've got a new piece of information now, and I can actually use that in part B if I want. So there's different equations you could actually use here. I'm going to go ahead and I'm going to use this equation. Displacement equals the initial velocity times the time plus 1/2 AT squared. So there we go. And I want to find, what do I want to find? The time. I want to find the time. And notice I've got 2 times here. It's the same time, but it appears twice. So sometimes that's a problem. Here it's not really a problem. Well, let's go through it. Let me go ahead and substitute in. So 402 meters, that's my displacement. My initial velocity is 0. So 0 times time is 0 plus 1/2. The acceleration is 3.7 meters per second squared. And I'm looking for the time, so t squared. So what I want to do here is I want to get t all by itself. So I'm going to take these 2 numbers, multiply them, divide it into that, and again, I don't want t squared, I want t. So the last mathematical operation I'm going to do here is I'm going to take the square root of this, which will give me t, and I'll take the square root of whatever, this divided by that is, and that's going to be my answer. So t, or time, is going to be 14.747. 14.747 seconds. I'll go ahead and I'll round off to 2 significant digits. So I'll round off to 15 here. I don't want to round off to 2 digits. So 15 seconds. There we go. 15 seconds. All right. Take a look at this also. I use this equation, but sometimes more than one equation works. If we throw up another equation here, average acceleration equals change in velocity over time. Go ahead and expand this. Final minus initial over time. Do I know the average acceleration? I do. Do I know the final velocity? I do. And try to use your unrounded off number there. Don't put in a rounded off number and then a round off again. You'll kind of get further away from what the actual answer is. So always take your unrounded off number, whatever number I had before I rounded it, and stick that in there. So in a sense, I have the final velocity, the initial was 0, and I can go ahead and solve for time. And when you solve, you should get the same number, So again, oftentimes there's lots of ways to do things. In fact, look at this. Average velocity equals displacement over time. Average velocity, initial plus the final, divided by 2 equals displacement over time. Once again, I can solve for time. I know my initial velocity. I know my final velocity. Again, use the unrounded off number. Divide that by 2. I know my displacement, 402, and I could solve for time. So there was 3 different ways I could have done part B here. Now, which is the best way? Doesn't matter. Whichever way pops into your head first, go with that. Go with that. This way happened to pop into my head first, so I went with this particular solution. But you know, this one isn't better than this one, isn't better than that one. Whichever one pops into your head first, that's the one you want to go with. All right, that's it for this problem.